What's up, everyone? We're going to begin Unit 7 with this video. This is Section 7.1. We're looking at the inverse sine, cosine, and tangent functions, all right? So I want to start by posing an equation to solve. Try to find 4 different solutions to the equation sine of theta equals 1/2 for theta in terms of degrees. And your answers could be positive or negative angle measures. So I have a unit circle here to help us quickly solve this one. We know that sine is going to be equal to the y-coordinate of our point defining our angle, right? So on the unit circle, the first place where sine equals 1/2 is right here, and that's at 30 degrees. Okay. Now rotate into the second quadrant. You can see that sine equals 1/2 again right here at 150 degrees. Okay. And those are not the only 2 solutions that you could give. Any coterminal angle to 30 or to 150 could be a solution to this equation as well. So that could be 390 degrees, which is coterminal to 30. That could be 510 degrees, which is coterminal to 150. Or you could even bring some negatives into play, like negative 210 degrees, which is coterminal to 150 degrees, okay? So what I'm really getting at here is this equation has an infinite number of solutions, okay? All right, so let's continue with this. One way that we could solve this equation is by using an inverse sine function, all right? If you think of sine as an operation that's occurring on theta within this equation, you could undo that operation of sine by using the inverse sine function of both sides of the equation, okay? So taking the inverse sine of theta is just going to yield theta, and then the inverse sine of 1/2, let's just see what a calculator would give us for that, okay? We would want to make sure we're in degree mode. So if I did inverse sine of 1/2, I end up with 30 degrees, okay? All right, so now the question becomes, how did the calculator know to give this specific answer of 30 degrees instead of any of the other solutions that we came up with on the previous page here, okay? Well, it all has to do with a restriction on the inverse sine function, okay? Recall, the original sine function, y equals sine of x, it's not one-to-one over its entire domain. It's not one-to-one because if you think of the graph of sine, it doesn't pass the horizontal line test, right? Now, if it's not one-to-one, that means its inverse cannot be a function, okay? So what we're going to have to do is restrict the domain of the original sine function in order for it to become one-to-one, so that the inverse will also be a function, okay? And doing this, restricting that domain on the original sine function, will allow us to only have one acceptable output for any input value in the inverse function, okay? All right, so let's look at the inverse trig functions of inverse sine, inverse cosine, and inverse tangent, all right? And for each of these, we're going to identify the domain and the range of them. And the range is really the important one. The range of your inverse function is going to be the same as the domain that you restrict the inverse function to have, so that it's one-to-one, okay? And I think it's important to understand for any inverse trig function, y, your output, represents an angle measurement, and x, your input, represents a real number. That's just the opposite of what it was for any original trig function, okay? So let's start with the inverse sine function. I'm going to pull up an illustration here, okay? So right now, I'm going to make it so that we just have the original sine function graph. This is f of x equals sine of x. with a domain of all real numbers right now, okay? And clearly, it is not passing the horizontal line test, right? Which means when I find its inverse, which is now the red curve here, that inverse is not a function, okay? And that's would be allowing for multiple outputs to occur using the same input value in that inverse function, okay? So what we want to do is we would like to take the original sine function, this guy right here, and restrict its domain in order to make it one-to-one, okay? Now there's an infinite amount of ways to do this, but the accepted mathematical way would be restricting it from domain values of negative pi over 2 to positive pi over 2, okay? Now I think we can agree that that is one-to-one. It passes both the vertical and horizontal line tests, which means its inverse would be a function, okay? So if we restricted the domain of the original sine function to be being between negative pi over 2 and positive pi over 2, then that can be considered the range of the inverse sine function, okay? And then just think the domain of this inverse sine function, it's going to be the same as the range from the original sine function, which is just from -1 to +1. So what this is telling me is that I'm only able to input values into the inverse sine function that are from -1 to +1, and they're only going to yield angle measures for the output that are between negative pi over 2 and positive pi over 2, okay? Now, I think it's important to understand that if you are an angle that spans from negative pi over 2 to positive pi over 2, you are either an angle in quadrant 1 or in quadrant 4, okay? So basically, we're allowing the outputs for this inverse function to be in this quadrant as well as this quadrant, okay? Now think about what that means for all students take calculus, okay? The sine function in the first quadrant is positive, and in the fourth quadrant is negative. So what you've done here is you've allowed for one quadrant where we're positive and one where we're negative, and then you've ruled out the other two quadrants where you're positive in the second quadrant and negative in the third quadrant, okay? Now, you might get confused as to why we have the fourth quadrant angles expressed negatively. Well, the reason for that is because you need to consider the um, the inverse function. You want to consider it as continuous, okay? So you're continuous if you go from negative pi over 2 up to positive pi over 2, okay? But you wouldn't be continuous if you try to go um, from the first quadrant, which would start at 0, and you'd be skipping the second and the third quadrants to then get into this fourth quadrant. So by skipping quadrants 2 and 3, the function wouldn't be continuous. So that's the reason for that, okay? All right, now we're going to do something similar for the inverse cosine function, okay? All right, so for inverse cosine, once again, not one-to-one, inverse is not a function. All right, so what we'll do is we'll restrict the domain on the original function, and it's accepted to be from 0 to pi. That makes it one-to-one, so that its inverse is one-to-one, okay? So the range for inverse cosine is from 0 to pi. Domain is from -1 to +1, all right? Now think about that range again. 0 to pi means you could be in quadrants 1 or quadrants 2 as an angle measure, okay? So again, think about what that means in terms of all students take calculus. Sine is positive, or I'm sorry, cosine is positive in quadrant 1, and it's negative in the very next quadrant, quadrant 2. So we're able to go from 0 to pi and make that a continuous function, okay? And then of course we rule out the third and fourth quadrants so that we're only allowed to be positive in one quadrant and negative in a second quadrant, okay? All right, and then inverse tangent function. Okay, so here's the graph of the original tangent function, okay? And let's see, if I restrict the domain of this to be 0 to pi, just like I did for cosine, okay, so that would be 1 to 1, okay, which means the inverse would be a function. However, it wouldn't be continuous, right? Notice that red curve there is broken up into two pieces, okay? So instead of restricting the domain from 0 to pi, we actually restrict it from negative pi over 2 to positive pi over 2, okay? And notice that makes the inverse a continuous function, all right? So the range restriction for inverse tangent is the same as it is for inverse sine, with one exception. This time, you cannot include negative pi over 2 and positive pi over 2 because you have asymptotes occurring on the tangent function at those values, okay? Now, domain is all real numbers for the inverse tangent function because the original tangent function has a range of all real numbers, okay? So in terms of quadrants that inverse tangent can be in, just like the inverse sine function, it's quadrants 1 and quadrants 4. You just can't be on the quadrantals of negative pi over 2 and positive pi over 2. Okay, so now let's run through some examples, okay? I would like to find the inverse sine of negative radical 3 over 2 without using a calculator, okay? So understand the input here of negative radical 3 over 2, that is representing the ratio for that we would have gotten as the output on the original sine function here, okay? So the negative radical 3 is like a y, and the 2 is like an r value here, okay? Now remember, inverse sine, it can only yield angle measures between negative pi over 2 and positive pi over 2, which is quadrants 1 and quadrants 4. Well, I can rule out angle measures in quadrant 1 right away, and the reason for that is because I'm evaluating this function with a negative number. So that means the output theta here must be in quadrant 4 by the range restriction, okay? So all we're going to do is just draw a quick little reference triangle down here for quadrant 4, and y is supposed to be negative radical 3, r is 2, that makes that, of course, 1. So we're working with a 60-degree angle here, but remember, the fourth quadrant angle, it has to be expressed in the negative direction, okay? So I'm going to say that inverse sine of negative radical 3 over 2 is equal to negative 60 degrees, or if we were asked for radians, negative pi over 3, okay? Most common mistake I get from students is instead of giving me negative 60 degrees, they end up giving me 300 degrees. And the issue with 300 degrees is it's not between negative pi over 2 and positive pi over 2, between negative 90 and positive 90, okay? All right, find inverse cosine of -1 without using a calculator. All right, so here, think of -1 as being over 1. We're working with cosine, so that's an x value, that's an r value. All right, and essentially we're going to be on a quadrantal here, okay, with the x value having the same length as the r value, okay? So think about the range for the inverse cosine function. It spans from 0 to pi, or 0 to 180 degrees. Well, the only place where cosine is going to be -1 would be over here at the point -1, 0. Okay, so that's going to be at 180 degrees, or at pi if we're in radians. Okay, all right, moving forward. Now let's evaluate inverse cosine of pi over 6 without using a calculator. Okay, so here this is like a composition. It's a function within a function. All right, so we're going to start with the inner function first. We're going to find cosine of pi over 6. Okay, now pi over 6 is the same as 30 degrees, right? So we could draw this out really quickly. 1 radical 3, 2. Cosine here is equal to, cosine of pi over 6 is equal to then radical 3 over 2. Okay, so now we take that result of radical 3 over 2 and we evaluate the outer function inverse cosine with it. Once we're here, it becomes very similar to the previous few examples, all right? So now I ask myself, inverse cosine, it can only yield angle measures in quadrants 1 and 2 by its range restriction. Well, I can rule out quadrant 2 here because I'm using positive radical 3 over 2, okay? So it's got to be a first quadrant angle where x is radical 3 and r is 2. And it just so happens the triangle I already have drawn is going to be the same triangle if I try to draw it again. So this is going to equal 30 degrees, or pi over 6. Okay. So it stands to reason then, right, that if I'm taking inverse cosine of pi over 6, then I can just effectively wipe those two out, and the result is pi over 6, right? The original input, okay? Well, that works in this case, but it doesn't work in the next example here, all right? So if I want to find inverse cosine and cosine of negative pi over 6, you can't just say right away that this equals negative pi over 6. Why? Because negative pi over 6 is not inside the range of inverse cosine, the outer function here, okay? My final result has to be a number between 0 and pi, or between 0 and 180 degrees, all right? So I'm going to approach this the exact same way I did the last problem. I'm going to start with cosine of negative pi over 6. Okay. Now that would be in the fourth quadrant, right? With a 30-degree reference angle. So here would be -1, radical 3, and 2. So cosine there is positive radical 3 over 2. I now take that result, I evaluate inverse cosine with it, and I'm going to get 30 degrees, or pi over 6, just like I did in the previous problem, okay, the problem above. So notice the result here is not the same as the original input of negative pi over 6. So you just got to be careful. You can't always say that inverse cosine of cosine wipes out always, right? Okay, moving forward, let's find inverse sine of cosine of pi over 6 without using a calculator, all right? So start with that inner function, cosine of pi over 6 is radical 3 over 2. We saw that in the previous couple problems already. So now I evaluate the outer function inverse sine with it. Okay, so inverse sine can yield angles in quadrant 1 or 2, right? Or I'm sorry, 1 or 4 by its range restriction. I can rule out quadrant 4 because inverse sine would have to be of a negative number for it to yield quadrant 4, okay? So think of this as a y, and this is an r for quadrant 1. So notice the angle measure here I'm working with, that's 60 degrees. So this is going to result in 60 or pi over 3 if we're asking for radians. Okay. All right, one final example. Find sine of inverse tangent of -4/5 using a calculator rounded to 3 decimals, okay? So this is another composition, but notice here the inner function is your inverse function this time. So it's going to yield an angle measure, and then you're going to evaluate sine of that angle measure, okay? So first it just wants me to approximate it on my calculator. That's easy enough. Let's go here, and we're going to find sine of inverse tangent of -4/5. You can see that's giving me -0.625 to 3 decimal places. Okay, so now let's try to find the value of this by hand, giving an exact answer, okay? So we'll start with the inner function, inverse tangent of -4/5. We said the inverse tangent function has to yield angles that are in either quadrant 1 or quadrant 4, from -pi/2 to +pi/2. Well, you're taking inverse tangent of a negative value, so that would have to be yielding a 4th quadrant angle by that range restriction. All right, so let's draw this out. Okay, so here's going to be theta in this direction, all right? And we know that y is -4, x is 5, and then if we used Pythagorean theorem, we could quickly find the r value to be radical 41, okay? Let me just verify that. There we go. All right, so clearly this is not a special right triangle here. You can't tell me what the value of theta is in exact form. The best you could do is use a calculator, right? But we're told we want to do this by hand. Well, here's the thing. You don't need to know the actual value of theta here to evaluate the outer function sine, okay? Now, to find the value of sine, I just look at the side lengths of my reference triangle over here, right? So sine always equals y over r, so that's -4 over radical 41. And then that gives me, in rationalized form, -4 radical 41 over 41. Okay, so there should be an exact value. If we approximate that, it should give me -0.625, just like the calculator did at the beginning of this example, all right? So let's just see here. If I took -4 square root of 41, and how about we just hit enter there? And then divide that by 41. See how we're getting the exact same approximation as when we put sine of inverse tangent of -4/5 into the calculator.